as you can see, we started with a solution that's actually shifted by 2 here, right? I mean, that's just to give us a sense of how to apply the boundary condition. If we didn't have a 2 here, okay, let's see, do we have a, yeah, so if we don't have a 2 here, let's look at the initial condition, and if we don't have a 2 here, I think the boundary condition is still set to 2, so we have this additional shockwave coming in, but like you can see that we have a shockwave forming, a discontinuity forming over here. And over here, the gap between the boundary condition of 2 and the solution here is also supposed to be a shockwave discontinuity. But because we are using a finite volume discretization, we can see that the shockwave actually gets smeared out a little bit. It becomes a very steep curve. It's not exactly a discontinuity, and that's because of the approximation error, right? So if you plot it if you plot it as a space-time curve, okay, the size of x, let's see, our x is this. Oh, right. So I think because the size of u, the number of u's in the spatial domain is 200, as you can see from here, but our x is actually there is a one more x than the number of averages. So we can't use this as the contour. So what we have to do is the x center. So let's compute the center of each domain is equal to x from 1 to n minus 1 plus x2 to n divided by 2. So that's basically looking at the average between the 2 endpoints of every finite volume to get the center. And let's do, when we do contour, let's use x center. All right. So that's actually our solution. Oh, let's actually start from our original initial condition and do this, right? So that's our solution in space-time. All right. Okay, so we can see that we have a positive part of the solution that moves to the right-hand side. We have a negative part of the solution that moves towards the left-hand side. And these straight lines are the characteristic lines on which the solution stays constant. Whenever you see the characteristic lines collide against each other, a shockwave, a discontinuity forms over here. Over here, because we have we set a boundary condition on the left to 2, the characteristic line over here has a slope that's actually even more shallow than the lines over here. So although you cannot see these characteristic lines because the solution here is constant, there are characteristic lines over here that actually collide into the shockwave over here, and that's another shockwave coming. Eventually, if you advance the solution forward, as we are going to do here, so let's actually, instead of a closed all, let's do another figure. If you advance the solution more, okay, so here, if you do a figure and u0 equal to u at the end, right? So eventually, so this is basically right after this, right? Continuation of this. You're going to see these two shock waves actually collide against each other, forms a single shock, even stronger, and moves to the right. All right, any questions on what we see numerically on the solution of the Burgers equation here? I don't know how to move this so I can. Oh, okay, good. So the solution here you can see is right after here. It's a continuation of the solution here. The y-axis are time, x-axis is space. All right. No questions? Okay. So one of the remaining questions we had after our last lecture was that how do we know that the finite volume scheme is capturing the movement of the shock waves correctly, right? How do we know that? So first of all, how do we know that how fast the shock wave is moving? And second of all, how do we know finite volume scheme actually approximates that correctly? So let's get to our first question.